This is part 2 of acid-base equilibrium concentration calculation. We will continue to use the ICE table and do the following example followed by a learning check. Formic acid, or HCO2H, is one irritant that causes a body reaction to some ant bites and stings. What is the concentration of hydronium ion and the pH of 0.534 solution of formic acid? So the equation for the formic acid when submerged in water is shown below. You have the formic acid plus the water forming into hydronium ion, and you have the conjugate base from the formic acid, HCO2. What we know based on the problem in itself, we know the initial value of 0.534 of the formic acid. So initially we have 0.534 molarity of formic acid. We don't have any hydronium ion nor its conjugate base of the formic acid. And there's going to be some change. And as time passes, there's going to be less of the formic acid, hence minus X, and X of hydronium ion, and the conjugate base of the formic acid has been formed. Therefore, at equilibrium, it's the top plus the bottom. So this would be 4 plus the bottom, which is just minus X. 0 plus X is just X, and then this is X as well. And that's pretty much about it. That's all the information that it gives you. But you can find additional information by looking at the dissociation constant of acid that's also located in your reference sheet. You should see this table, and it gives you all the name and the formula of the weak acid. Most of them are weak, except for one here, one or two here. And you will notice that you can find formic acid right here. You see that? That formic acid has a Ka value of 1.8 times 10 to the negative 4. So the Ka value is 1.8 times 10 to the negative 4 for formic acid. So we actually have two information: the Ka value for formic acid and the concentration initially of the formic acid, and this is enough for us to find out the concentration of hydronium ion and the pH. So let's continue. I'm going to go ahead and take this table out so that we have more space over here. All right, so let's set up Ka. So Ka is equal to concentration of hydronium ion and HCO2 minus all over the HCO2H. Okay, and we're going to go ahead and plug in the values and the X's. We know Ka is equal to 1.8 times 10 to the negative 4. The hydronium ion is X times X, and then the bottom is 0.534 minus X. Now we can go ahead and multiply this through, but before we go on and doing additional algebra, notice that the Ka value is quite small, is less than 0.001. And if I had mentioned, I don't know if I mentioned to you before, but if it's less than, if the Ka or Kc value is less than 0.001, then we can neglect this X that's on the bottom as if it's negligible. So therefore, it becomes 1.8 times 10 to the negative 4 equals X squared all over 0.534. Now we can continue on. Let's go ahead and multiply 0.534 both sides. And this will cancel out. If I were to take that and Punch it into the calculator. 0.534 times 1.8 times 10 to the -4. Then I end up with 9.612 to the -5. And then we're going to square root that, as you will see in a moment. We'll have to square root this. Yeah, 0.0098. Okay, so what I have done prior to this, so this is 9.615 times 10 to the -5 is equal to x squared, and then I square rooted this. And by square rooting this, I get x is being equal to 0.0098. Now, what is this talking about? Is this K? Is this concentration? Concentration of what? Well, you notice that X represents a concentration of ammonium, hydronium, and the HCO2 minus at equilibrium. So at equilibrium, we know that we can already found the concentration of hydronium ion. So this is H3O plus. It's also asking for pH. If I want to know pH, we know that pH is equal to the negative log of concentration of hydronium ion. And if I were to punch this into the calculator, you should get 2.01. Now let's do a learning check based on what we have learned so far. Try this and come back and check the video. It's much similar to what we have done previously, but the only thing that is different is we're not dealing with an acid, but we're dealing with base. But Kb is given here for the trimethylamine, which is right here on the very bottom. So it has the Kb. And it also wants to know the POH, not just pH, but POH. So see if you can try this and come back and I'll explain a bit. And here is the key. So you'll notice that I got the Kb from this table, the trimethylamine, and that's how I was able to solve for X. When I solved for X, I realized that the Kb value was really little, so I was able to ignore this minus X portion. When I got the concentration of the OH minus, I could put that into the POH equation to get the POH. Not pH, but POH. So that was POH over here. We know that pH and POH has to equal 14. That's shown below. So therefore, I was able to get the pH. And so those are the three questions. That's what we were trying to look for. The hydroxide ion concentration, POH, and the pH, which is all listed here. In this example, let's go over additional acid and base equilibrium concentration. Here it says sodium bisulfate NaHSO4 is used in some household cleansers as a source of a HSO4 negative ion, a weak acid. What is the pH of a 0.50 solution of HSO4 minus? So you'll notice that on the very right-hand side, there is a table, which is from your reference sheet. And if you were to look for HSO4 negative, you wouldn't find it here on this formula. But you do find something really close, which is H2SO4. Well, this H2SO4, or the sulfuric acid, you'll notice that there is hydrogens and right here, and there's two of them. That means this hydrogen is able to donate its hydrogen so that it becomes HSO4 minus. So hydrogen has been donated somewhere. But the hydrogen can further be donated. So there's additional hydrogen that can be donated in order to become SO4 2 minus. So we can say that the sulfuric acid is a polyprotic acid, meaning it has the ability to donate hydrogen more than once. And so therefore you would get different Ka values. This represents a Ka value for the first round, and the second round, it shows the Ka value for the second round. And as you can see, for this particular formula, you see that the Ka value for this one would be the second round of Ka value because it's starting from the HSO4 negative. So the second Ka2 is 1.2 times 10 to the negative 2. So Ka for this is 1.2 times 10 to the negative 2 for this particular weak acid. Okay, let's erase that so that we're going to need a lot of room to do this. I'm going to set up an ICE table, and the starting value for the first weak acid is 0.50. Then these are zeros. Then you subtract the X as a change and add the X as a change on the product side. And add the top and the bottom together, showing the equilibrium. So therefore, we can say that Ka is equal to the concentration of hydronium ion, concentration of SO4 2 minus, all over HSO4 minus. So let's plug in some values and all the variables, okay? And I will do that right here. We know that Ka, therefore, is equal to X times the X all over 0.50 minus X. Ka value is 1.2 times 10 to the negative 2. So that's, if I were to write that out, it is 0.012. So this is actually a quite big Ka number. Remember, if it was lower than 0.001, then we can ignore the X here, but we can't because the Ka value is a little bit big. 0.012. I'm going to multiply by the top, the X's, so that's X squared, and then we have the bottom denominator portion. We're going to multiply the denominator portion both sides. And then we can cancel out these guys. Let's go ahead and distribute. And then this is 0.012x to the x squared. If you distribute this one, this will be 0.0060. Okay. Now I want to put all on the other side. So I'll put this on the 0 on this side. That means I need to add 0.012x. And then if I move this one over, it's subtracted 60. This is setting up for that quadratic formula. Remember that ax squared plus b x plus c, it has a quadratic formula of x equals negative b plus or minus square root b squared minus 4ac all over 2a. So if I were to plug all the values in, so that would be b is your negative 0.012 plus or minus, and then you would get 0.012 to the second power minus 4a is 1, and c is that 0.006 negative. Sorry, I had to squeeze that in there, and then 2, 1. Now, if I were to calculate this out, which I can, let's go ahead and do that so I can just show you real quick. And so I'm going to target everything that's underneath that square root first. So that would be 0.012 to the second power. And you're going to subtract that with the 4 times the 1 times negative 0.006. So that's what's underneath this square root. And if I take the square root of that, I would get 0.155. 0.155 plus or minus negative 0.012. Now you have to think about it here. Do we use the positive or should we use the negative? We know that x has to be a plus x. So therefore, we have to use the positive value or we'll end up with a negative x. So we're going to go ahead and scratch this one out and go ahead and solve for that particular portion. So it's negative 0.012 minus the plus the 0.155, and then that is divided by 2. And I get 0.0715 molarity. Now this is showing you the concentration of the products, so HCO3 plus and SO2 minus. So those are the X's. So, but what's most important is the hydronium ion because we want to know pH. And to know pH, pH is equal to negative log of the hydronium ion concentration, which is 0.0715. And I get 1.14 as my pH. Now this learning check, I'll leave this up to you. You'll notice that the caffeine will not be on that table that is shown or in the, it won't be on that chart. But I've already given you the KB here, the value. This should be multiple. So try this and come back and check your answers. And here is the key.